Okay, I think we can get started. we have most of the people who are going to attend, and I'd just like to welcome everybody to today's webinar. My name is Ethan Donald. This webinar is brought to you by Peel 3D and Exact Flat Software, and I will be your host and moderator today. Our topic is how to make paint protection film templates and vehicle wraps fast with 3D scanning and digital pattern making. In our example, we're going to be showing how to process a scan. And I will say that the scan that we're going to be looking at is going to be this vehicle here. It's a late model Hyundai, and it is a good example for us because it's not too much surface area to scan, and it's easily visible with the colors that are there. In terms of the process we're going to be using today, this process applies to all soft goods, particularly paint protection film, vehicle wraps, vehicle covers. It could be used for interiors such as seating, dashboards, console panels, and a variety of other things, depending if your business is paint protection exclusively or if it is paint protection as well as to other parts of automotive interiors. A few housekeeping items before we begin. First of all, we are going to record this session. So we will give you a link in the next day or so for you to share with your colleagues or to review again. Just a reminder that this webinar is in listen-only mode, and there is a chat feature and a question feature in your control panel, and you can use those for questions. We do have some people standing by that are ready to answer your questions, and approximately 45 to 60 minutes or so, we should have you through the session today. I'm going to be joined by panelist Libya Guerra from Peel 3D. She's the business development manager for Peel 3D, and Marie Simard. Oh, pardon me, I got a little mistake there in your name, Marie. But Marie Simard is the US accelerator for Peel 3D, and I'm joined also by colleague Mark Jewell, who's a VP of Product Solutions at Exact Flat. All participants here have experience with the workflow that we're going to be taking you through today. And I'm also joined by our senior engineer at Exact Flat, Luke Naransky, who's going to be taking you through the live portion of the demo. We're going to cover as much as we can in terms of the workflow. There are three broad steps involved in making templates. The steps are, first, we scan in 3D. The next is we process the scan and defeature elements that are not useful for making templates. And the last thing is we convert from 3D to 2D to create our templates. This is the process that is used both by aftermarket template makers who make templates for vehicle wraps. It could be graphical templates or just paint protection templates, as well as OEM providers like 3M and others. This is exactly the process that they use to make their templates. So with that being said, I am now going to start the portion of this demo. I will say that we're gonna highlight some of the best practices here. So I'll ask Luke and team to call out these things: the correct scanning technique, the best practice there; how to easily smooth surfaces in situations where you need to split a scan into pattern pieces. We actually won't be doing that today, but if you have a more complex paint protection project where you're going to be doing a full vehicle or you know, larger sections of a vehicle, this is certainly we can show you a best practice there. The other best practices are how to make perfectly symmetrical parts. These are parts that are mirror images of one another. It saves a lot of time, so you don't have to scan the whole vehicle. You can just scan half of it and then mirror the part that you scanned. And then how to adjust templates for stretch. Now, this is depending on the type of film that you're using. Sometimes you'll adjust for stretch, sometimes you won't adjust for stretch. So these are just some of the big 5 best practices that we've laid out here. In terms of the demo, it's a lot of work to get through in this session. So what we're going to be doing is we're going to start off with a quick video summary of the setup of the scanner and the scanning process itself. Once we've completed that, we'll go to section 2, which is the processing of the scan, which will be done live by Luke, and then creating the templates themselves, which will be done live by Luke as well. So if you bear with me for just a moment, I'm just going to start us up to get our video going here. Here we have the carrying case from Peel 3D. You can see the Peel logo on the side there. We're going to do a quick unboxing with my colleague Mark Jewell. And as we open up the container, we can see the unit there on the right-hand side. The Peel to CAD scanner comes with 3 cameras, one camera at the top, one there in the bottom right. In the middle, we have a light source or emitter, and on the left-hand side there is the color camera. We'll just put that on the table. In addition, we have the connecting cable. This is the cable that connects your scanner to the computer. We'll get back to that in a little bit. We also have a power source. The power source does come with multiple adapters for different types of electrical receptacles and voltage systems throughout the world. And that is the USB key that has the documentation and the software. Lastly, we have targets. These targets are used on highly reflective surfaces to improve the accuracy of the scan. And that's the unboxing. Now let's get into setting up the unit. Now let's go ahead and set the unit up. First, we're going to connect the power cable to the power source. And the power source cable will be connected to the scanning cable. We'll look for the Y connector or the pigtail end and connect the power source there. Following that, we'll connect the USB connector to the computer. And following that, we'll connect the other end of the Y connector to the back of the scanner. You can see there's an arrow in the back here. We'll just connect that to the back of the scanner, just to line it up, plug it in. When you do that, the blue light indicator on the back will indicate that the scanner is ready to go. Another way that you can check to see that the scanner is ready to go is by looking on your computer. The indicator in this position will change from red to green. And now we can start the calibration process. In order to calibrate the Peel 3D scanner, we're going to use the Peel 3D calibration plate. However, we will not be doing it in this session. We'll just show you the plate here. The plate consists of a set of targets arranged in a pre-calibrated array, which you'll scan to calibrate your scanner. It's very important to keep it safe and not damage the scanning targets themselves, as they are specifically designed for calibration. Now it's time to place scanning targets on our surface area. We use a hand span as a general guideline for how to array our targets that we place on the surface area. You can see that we also want to make sure that we're placing some targets that are close, but not necessarily on the boundary edges of the surface area that we want to scan. We want to make sure that the targets are placed randomly. You do not want them placed in a pattern of any kind. They should be randomly placed, and they should be more or less evenly spaced throughout the surface area of the object that you're trying to scan. The Peel 3D scanner can scan in 3 modes. One is a geometry mode, the second is a target and geometry mode, and the third is a texture mode, which will pick up color or textures. In this particular situation, we're going to use the geometry and target mode. The targets will assist us in helping to get a good scan. We're going to only scan half of this car bumper because it's symmetrical and we can easily mirror it. And you want to make sure that the scanning targets are not placed on areas that are going to be excluded from the scan. We'll just put a few more targets down here, make sure that we got good coverage. There we go. And you'll get a feel for how many targets to use. Sometimes it's only necessary to use targets in more difficult areas, or maybe, for example, in shiny and reflective surfaces. In those situations, you can also use a powder to help. But here, we're just going to use targets. We are now ready to begin the scanning process. We're going to start in the center of the bumper and make our way from the right to the left. We'll start by pulling the trigger on the scanner, and the emitter will give us a general direction of where the scanning is taking place. It is important not to scan too closely to your surface or scan too far, as we are demonstrating here. The optimal distance is about 30 centimeters from the object, and you want to keep the scanner in constant motion. Even if you're new to scanning, this particular surface that we're
scanning today will only take about 2 to 3 minutes. And even inexperienced scanners can produce very good results. Now we're just going to go over and scan some of the areas again. You want to scan in such a way that you do not have a resulting scan that has holes or misses detail because you've scanned too fast. Once again, you orbit about 30 centimeters from the surface, keep the scanner in constant motion, and you should get great results. If you're currently applying your paint protection film by hand, you'll be very happy to know that the templates that come out of this scanning process are very accurate, and you can make more of them as you get more vehicles of the same type. That should save you a lot of time. And we're just about finished the scan, and it's maybe 2.5, maybe 3 minutes long for the scan. And as I mentioned, we only scan half the bumper because we can mirror the geometry post-scanning. And that's it. 3D to 2D scanning. We're now going to process our scan in the next step.
So hello, I'm Luke. We're going to be looking at the scan. So this is the output of the raw scan file that was captured by Mark, and we are looking at this in the Peel software right now. So immediately after scanning, we've got raw data, and this data needs to be processed using the Peel software before we can flatten it with exact flat. The type of things that we need to do to the data is, first of all, we need to trim away the excess data that we no longer need. For the purposes bumper, we are going to be focusing on this main part here. So from the scan video, this would be the green colored part. We're going to trim away everything that was below it, and we're going to trim away this excess up here and on the sides. The amount of time required to do all this processing can take about half an hour. So I'm not going to process the entire file. I'm going to show you how we would process that. But once fully processed, you would expect your mesh to look something like this. So this is a mesh that I've already fully processed, and I've gone through the steps of cleaning it up. And so this is what our fully processed mesh would look like. So I've trimmed away all of the excess data. I've smoothed and sanded the surface of the model. I've trimmed all the edges so they're nice and clean. And I've extracted the patches here for the cutouts. So this is what our end goal is what we want our goal to look like. We start with by creating a mesh. And once we have our mesh, I do apologize. When you scan the data, it comes in, it's not oriented yet. So our last step is going to be orienting the data. So it comes in any kind of orientation. So you just orbit around and get the best view to work with the data that you need. So the first step is to trim away the unwanted data. And there's a couple different ways to do that. Probably the easiest way I've found to do it myself is to simply select a bunch of triangles here and just remove them. So we're going to use our freeform selection tool here. And I'm just going to draw a selection path, and I'm just going to select all these triangles here. And then I can just delete them by pressing delete on my keyboard. And we would repeat this process for all of the remaining selections. We can just keep selecting all the way up along this path here until we've selected all the triangles that we no longer need, and then we can delete them. We're still left with a bunch of floating islands out here, and these are pretty easy to deal with. The way we're going to do that is we're going to use our connected selection tool. We're going to select the main body of the mesh, and then we can simply invert our selection. So this is going to flip the selection. So now I've got all these little islands selected, and I can just delete those. So that's the easiest way to deal with those. So we would repeat this process. We'd continue selecting all the triangles along the perimeter that we no longer need until we only have the main body of the mesh that we're looking for. Once we've done that, we can then start to process and condition the boundary of the mesh. We can fix it up to smooth it out. We want to make sure that we have a very smooth boundary. If we were to try and flatten something like this, then our pattern would have this characteristic there, so we want to smooth this out. And the way we're going to do that is we are going to use the Edit Boundary tool. Using this tool, we can edit the entire boundary of the pattern piece, or we can change to partial boundary, and this is the tool that we're going to use right now. With this tool, you pick a starting point, you pick a stopping point. I'm going to pick somewhere down there, and then you pick a point somewhere in the middle, and that's going to allow you to choose your boundary that you're going to work with. We can manipulate the curve tension, and we will see a preview of the curve. As we manipulate the tension, we can now see we've got our green preview there. If I apply too much tension, it's essentially going to create a straight line between my start and stop point, which we don't want. So we just manipulate the curve tension until we get a nice smooth curve flowing between our points. And once we have the desired tension, we'll back it off a little bit here. You go ahead and click apply, and the tool will go ahead and manipulate the boundary for us and smooth that out. We can adjust the analysis layers here, and that will also help us smooth out that boundary as well. After the tool, you might have to do a bit of cleanup depending on the quality of the scan, but this is essentially how we would go about processing our edge to smooth out the edge. Once you've fixed all the edges, we'll go ahead and close that. You can then start to smooth out the surface of the mesh. So right now, as we look at this, we can see we've got a bit of an orange peel effect going on the surface. And for rendering visualization, this is fine, but for flattening, we don't really want all this texture on the mesh, so we want to smooth this out. There's two main tools that we use to smooth this out. The first is the sandpaper tool, and the second is the de-feature tool. Sandpaper is fairly self-explanatory. It basically treats your mouse as a piece of sandpaper, and as you move your mouse around the surface, I'm just going to increase my brush size here, it's essentially going to sand the surface. So as I do this, we can see all that texture is disappearing and is being smoothed out. So we want to go over the entire surface of the mesh and smooth out as much of this detail as we possibly can. Our goal is to make the surface of the model look as smooth as possible. That way we don't have huge amounts of detail that's going to be captured by the flattener. For larger areas where you might have holes or anomalies in your mesh, we can deal with those simply by using the de-feature tool. And this works very similar to trimming the boundaries. We're once again going to go to our freeform selection tool, and we're going to use it to select an area where there might be a very large anomaly. It could be a spike in the mesh, it could be a sunken hole, or it could be malformed geometry. We want to select those triangles. As a best practice, I always recommend increasing your selection area once or twice. That's going to help select any triangles that were hidden on the interior that you can't see. There might be a cavity or something, so you want to increase your selection area to make sure everything on the interior is selected. And then if you want, you can back off your selection again and then use the de-feature tool, and that's going to basically rebuild the mesh within that localized selection and get rid of that unsightly feature that may hamper the flattening process. If you have any kinds of holes in your mesh, you can fill those in again. So as we move around our boundary, you might find it's a little difficult to rebuild some areas of the boundary depending on the curvature of the surface. So if you have a hole in your mesh, we can fill that in. If you have a hole on the boundary and as you're trying to rebuild the edge, it's sucking in your rebuilt edge too much, you can do partial fill as well. So for this edge right here, if we want to get this a little bit smoother first before we rebuild the edge, we can fill in part of the boundary here using a partial fill. So when we're using the fill hole tool, we can do a whole hole, or we can do a partial hole, or we can do a bridge. We're going to focus on these two, and for this example, I'm going to use partial. And this works very similar to rebuilding the edge. You pick a start point, you pick a stop point, and then you pick somewhere in the middle, and the tool is going to fill in that partial hole for you. So by filling in this partial hole, if you have a very huge gap in your part, you can partially fill in that hole, and that's going to make it easier to then repair that entire boundary. If we zoom out and if we come to an even larger hole, we've got a hole right here in the mesh. If we wanted to fill this in for processing, we can do something similar. We can open up the hole tool. We can select the hole mode, and then you just select the boundary and the tool will fill in that hole for you. Once you've finished sanding your mesh, you've filled in all the holes, you've trimmed off and repaired the boundaries, we can then go ahead and mirror the model. The easiest way to do this is to, first of all, orient your model. And it's also a good idea to orient your model that way downstream in Rhino. It's a lot easier to manipulate the model. There's a number of different ways that you can orient your model. Probably the fastest way to do it is to work in terms of reference planes. So I'm going to orient my model. So this face here is more or less orthogonal to the XZ pattern plane. And I also want this edge here to lie directly on my XY pattern plane. So I'm going to accomplish this by creating two planes first on the surface of my model. I'm going to create one on this face here, and then I'm going to create a plane where this edge is coincident with the plane, and then I can orient my part so the XY and the XZ pattern plane align with those two reference planes. Thankfully, the Peel software has some fantastic tools to help us with this. The first one that I'm going to use is my simple brush selection tool here. And I'm going to just decrease my brush size slightly here. And I'm going to use this to simply select some of the triangles right here in this area. We can see the screw holes here for where the license plate used to be mounted. So we know that this area right here should be the center line of the bumper. So that's why we're going to be creating our plane in this area. So I'm just going to select some of the triangles in this area because this should be fairly planar. And now what I can do is I can go to my basic entities option here, and I can create a plane. And using the different modes available to us, I'm going to use the triangle selection mode, and that's going to best fit a plane to my selected triangles. So we'll go ahead and we'll create our first plane using that technique. For the second plane, I'm going to change my mode to vertex selection, and this allows me to create a plane by selecting 3 different vertices. I know that I want my plane to lie on this break right here, so I'm going to pick 3 different vertices along this break, and so long as these vertices are not coincident, as in they don't form a straight line, I will be able to create a plane on that surface right there. So now we have our 2 different planes. So we'll go ahead and close the tool. And at this point, we can use a basic alignment to align this part. We're going to align to plane, or sorry, rather align entity-based alignment. And this allows us to pick a couple different constraints. Our first constraint, we're going to pick the first plane here, and we are going to align this to the XZ plane. And our second one, we're going to pick plane 2. We're going to align that to our XY plane. Now the part's being aligned dynamically as we do this, so we're going to orbit around and try and get a better view now that we've mostly aligned it. And as we look at this, we can see that our Z-axis is pointing down. So what we're going to do is we're actually going to flip the orientation of our XY plane, and that's going to flip the part essentially. So now our part is up. We can also see that we are now looking down the positive axis of the y-axis. So we're going to invert this other one as well. And once we do that, we now have our part correctly aligned. So we'll go ahead, we'll click the align button, and we'll accept those changes. Now it's going to be a little easier for us to mirror the part, and downstream in ExactLab is going to make it a lot easier for us to process and flatten this part. In order to mirror the part, we're going to use the mirror mesh function here. And this mesh is this function is pretty simple to use. We're going to use the draw line method. And the reason why I like to align the part first is that allows me to click this button right here, which is going to align my mesh. So we're looking straight on at the positive y-axis. As we go to align, we're going to use the draw line, and we don't have to be absolutely perfect with our selection here. We just have to get close enough, and we use this tool the same way we select our parts. We just hold Control on the keyboard, and that allows us to draw our line. We're going to do a best fit line here, and that's going to create a plane. So if we now rotate around, we can see our plane there. And when we click apply, we're going to choose mirror and sew. So this is going to mirror the part and it's going to sew the two together, so we can expect to have one single output mesh. And when we click apply here, after the tool does its magic, we now see that we have a mirrored and sewn part. Because we chose to keep the original mesh, we're still looking at the original, but we now also have our mirrored mesh here. So if we turn off the original, this is the result of mirroring our mesh. So after all of this process work, after we've finished absolutely everything, we can expect our mesh to look like this. The last step is to export our mesh. We can select our mesh and we can go to File, Export, and we can export the mesh and we can save it as either an STL or an OBJ file. Both file formats work extremely well with ExactFlat. So go ahead and export your mesh and then we can import it into Rhino. When we import it into Rhino, we have a mesh that looks very much like this. So this is the result that we were just looking at, our mesh here. I've taken a couple extra steps for this particular model. I've also filled in the headlight and I filled in the holes for where these cutouts were. But I've also created a curve. Pardon me, do that. I've also created curve representations for where those boundaries were. I want to keep these cutouts or these curve representations because we do want these features to be on our pattern, but we don't want to be flattening those cutouts because they add unnecessary complexity to the flattening process. So instead, what we're going to do is we fill in the holes and then we trace the location of those cutouts on as curves afterwards. This is going to become a little more clear towards the end of the ExactFlat process when we can see the tracing process in operation. So the first thing we're going to do is we want to decimate our mesh. The results that come out of Peel, they're very detailed. This particular mesh has about 200,000 to 300,000 triangles on it, so we want to decimate this to a reasonable level. We're going to do that using ExactFlat's adaptive remesher tool. So we're going to switch over to the Mesh Tools tab. We're going to click the adaptive remesher. Pardon me, I'm just going to load the ExactFlat plugin first. Load plugin. So now we can use the ExactFlat adaptive remesher. And we're just going to use default settings. For the purposes of this demo, I'm going to use default settings. If I was doing this in a production environment, I would probably lower my desired boundary and minimum edge length tolerance. And that's simply to give me a resulting mesh that does not distort the curvature of the mesh. I do have an example of what that would look like, and I will show you that example after we've finished this remeshing session. But for the purposes of this demo, I'm going to use the default settings, and we can examine the difference between the two as well. So right now what's happening is the tool is analyzing the curvature of the mesh. So it's analyzing every single vertex on the mesh and it's building a representation of the curvature, and we're essentially going to be replacing or building a new mesh over top of the original. So by the time we're done, we're going to have taken our mesh that has just over 270,000 vertices, and our resulting mesh is probably going to have about 800 vertices. So this is just going to take a moment, and pretty shortly the tool is going to finish and we will see the result. And there we go, the tool is finished. So we've taken our input mesh that had about 280,000 vertices, and we've reduced this down to about 733 vertices. So as an example, if I were to tighten up my tolerances to better preserve the curvature, specifically down in these areas here, I would use different settings, and this would be an example of the settings that I would choose. So we do have more triangles on this particular mesh here, but as we can see, we're conforming to the original curvature of the mesh much better. When using the adaptive remesher, you want to find a balance between the number of triangles on your mesh. As you have more triangles in your mesh, that will affect the speed of ExactFlat. So that's why we're using the default settings for the purpose of this demo. Once you finish the adaptive remesher, we can then go ahead and flatten the mesh. We're going to switch over to our Tools tab of the ExactFlat toolbar, and we're going to use the Flattening tool. This tool very quickly creates an initial unoptimized 2D flat pattern. We can see that mesh right here. So at this point, we are going to switch over to our ExactFlat pattern layer. ExactFlat puts both the flat pattern and the reference model on a separate layer. So we're going to make the ExactFlat pattern layer the default, and we're going to hide everything else. I'm also going to leave my perspective viewport, and we're going to focus on the top-down viewport. We can see quite a bit of information just from this pattern. The color tells us roughly how much strain we have on the pattern. And as we look at the mesh, we can also see we have this cross mark here. We use color to represent the strain on the pattern piece, and that's probably the primary indicator of the quality and the accuracy. If our part was pure white, that would tell us that we don't have any strain. As we move through the spectrum, cyan represents up to 5% strain, green is up to 10%, yellow is 15%, and red is 20% or more. So as I look at this mesh, I see a lot of red, I see a lot of green. That's telling me that if I were to cut this pattern out right now, I'd probably have to stretch the material over 20% just to get it to fit. That's okay though. ExactFlat operates as a two-stage flattener, and we haven't finished the flattening process yet. The first thing we're going to do is we want to use one of our pre-flatteners. We have many different pre-flatteners here. So for this demo, I'm going to use our fracture pre-flattener, and we are going to use this to accomplish two things. First of all, we want to fix this cross mark here. This represents a fold or wrinkle or an area where the pattern's been pinched and the material might be folded over on top of itself. We fix those using pre-flatteners. And second, I want to press as much of the strain out towards the edges of the pattern before I start the optimization process. So I'm going to pick a spot right here in the middle, and we can see the tool pressing all that strain outwards. We no longer have our fold or wrinkle in the corner here, and we can see from the color that we've greatly reduced the strain on the part down to much more reasonable levels. We have mostly white everywhere with a bit of cyan, and in a small localized area we have some red here. So this is an ideal starting point. The next step, we're going to use the optimizer. This is the second stage of the flattening process. So we're going to use this to optimize the pattern piece to minimize the strain and sag. At this point, we're not going to change any of the defaults for this demo. We're just going to go ahead and use defaults, and we're going to start the optimizer. So very quickly, we're going to remove or further remove strain from the pattern. And we can tell that just visually by watching the colors change towards more white. We do have quite a bit of information displayed here, and probably the most important one would be the average energy density. That's this number right here. And this tells us the global average amount of strain on the pattern piece. To put that into perspective, if we had on average 1% strain on the pattern piece, that would be this number here. So we would expect to see about 0.4 Newton meters of energy on the pattern. Comparing that to the average energy of our pattern, 0.08, that tells us that we have well below 1% average strain on the pattern. So we've got a very good, very accurate pattern here. So we'll go ahead and we'll click OK. Depending on the material that you're working with, some films are very stretchy, others are very rigid, and depending on the film you're working with, you might have different needs from your pattern or different application techniques. And some films, it's desirable to shrink the pattern a little bit. That way you do have to stretch it. We can do that using ExactFlat, and in order to do this, we need to first place a grain line or a grain orientation on our pattern, and we're going to use that using our grain line tool. I'm going to pick an edge right here in the middle of the part, and this allows me to assign my stretch or my shrinkage with respect to the grain line. To do this, we're going to turn on the global target strain option here, and we can apply strain in two different orientations. We can apply principal strain, which is in the direction of the grain line, or we can apply transverse strain, which is perpendicular to the grain line. For the purpose of this demo, we're going to apply principal strain, and we're going to apply about 2.5%. The value you use may depend entirely on your application needs or techniques or the material that you're working with, but for this demo, we're going to use 2.5%. Now that I've created my grain line, I can re-optimize my pattern piece, and this time it's going to optimize with that stretch in mind. So we're going to run the optimizer again, and very quickly we're going to come to the end, and the very last step here, we're going to apply that strain. So just visually, again, we can tell that now instead of a pure white pattern, we have a light cyan pattern, so that's visually telling us that we have about 2.5% strain on our pattern piece. We can confirm that just with the average energy density here. Again, if we had on average 1% energy density, we'd have about 0.4. We're up to about 1.1, which is approximately 2.5% energy density. The last step here is we want to recreate the cutouts for the headlight and the utility ports here. Because we flattened this as a single piece without the cutouts, we need to add them back on. So to do this, we're going to go back to our 3D model. So we'll go back to our perspective view. We're going to turn on our exact flat model, and we're going to turn back on our cutouts layer here. So this is where I have these curves that represent the cutouts for the headlights. We're going to use the exact flat trace tool, and we're going to trace these cutouts onto the pattern mesh. So I've activated the tool, and now I'm selecting my different curves here. And I'll select the headlight. Depending on the model of the vehicle, you may only have the cutout on one side. It may be on both. Because this part was mirrored, I had the cutouts on both sides. So at this point, it's up to you whether you want to trace them onto both sides or only one side. For the purpose of this demo, I'm just going to do one side. I'm going to select my target model here, and because I'm working with polylines and not splines, I'm not having to tessellate my curve, so I'm just going to go ahead and click OK. And very quickly, I've transferred those cutouts onto the 2D pattern. So at this point, we have our flat pattern, and we can export this pattern to a DXF simply by clicking the export button. So I'm going to call this webinar bumper, and we'll go ahead and we'll export that, and then we can bring the pattern in and have a quick look at that. So this is the result of the bumper that we just flattened. And that's it for the exact flat portion of this webinar.
All right, Luke. Thanks for that. I just want to have a quick conversation, Luke, about the best practices that we talked about previously. So let's just start at the end. So you used the target strain to adjust the templates for stretch.
Correct.
Some film requires or is typically stretched when it's applied, and some film is not stretched when it's applied. If you use the target strain mechanism, it's pretty easy. But if you don't use target strain, are there other ways that you can adjust the size of your template?
Yeah, if you don't want to use target strain, you can simply scale your model before flattening. It might be a little more difficult to find the scaling factors required to get the exact amount of strain. So with the target strain, you're telling it how much strain you want to be applied to your part in order to get it to fit. Whereas if you're scaling it, you're having to specify a scaling factor like 90, like the scale at 99%, 98% or so. So it might not be as simple as using the global target strain, but there are alternatives if you don't want to use the global target strain.
Okay, and just so that everybody's on the same page, when we talk about strain, we're really talking about elongation, right? The amount that the pattern has to elongate in order to fit properly. So those areas that you showed where the pattern had lots of red or other colors, those are indicative of situations where that particular section really needs to stretch or elongate in order to fit properly. Can you just talk a little bit about that?
Yeah, so the amount of strain on your pattern piece is probably best described as how much shrinkage has occurred on your pattern. So the more strain you have, the more your pattern has shrunk relative to the surface area of the original 3D piece. So in a perfect world with a perfect pattern with no strain, the surface area of your pattern piece would be identical to the surface area of your 3D model. But as you add more and more strain to your pattern, the surface area of your pattern will decrease relative to your 3D model. So the more strain you have, the more you're going to have to stretch it and elongate your pattern to get it to fit the original surface area of the 3D piece that was scanned.
Okay, so there's one other question I have along this line, and that is material properties themselves. So different types of film will have different stretch characteristics. And while ExactFlat does come with a database of common materials, if you wanted to have those stretch characteristics of your particular film applied to the flattening algorithms, just talk a little bit about that if you wouldn't mind, please.
Sure. So we do have a material library, and we can choose different materials for use during the optimization process. We do use the mechanical properties of those materials. So each material in our library has been analyzed at a lab. We've stretched it along the warp, weft, and bias direction to determine how it behaves as the material is being deformed. So I didn't change the material during this demo, but you can choose the material that you're going to use for optimization. And we do have a way you can use our material editor to insert your own custom materials. We do partner up with the lab. They do produce a very nice report. It very clearly tells you all the information you need. So if you do choose to have your material analyzed, you can open up our material editor. You go to File, New, Create from Analysis. The report is very clearly going to tell you the Young's modulus, bias, X, and Y values. So you literally just copy them from the report into this dialog. You give it a thickness, a name, and then you click OK, and you will have a new material according to your a new material in ExactFlat for you to use.
Okay. All right. So thanks. That's very helpful. So with respect to creating symmetrical parts, now this particular scan was not that difficult. It was a straightforward scan. The bumper was not that big. We could have chosen, if we had wanted to just put targets on the whole bumper and scan it. Wouldn't require to mirror it. Now, can you just talk a little bit about the trade-offs between larger complex parts that would be more difficult, would increase the scanning time versus just mirroring the part digitally? If you can just maybe make a few comments about that, Luke, as well.
Sure. So obviously scanning takes time. So if you can save some time by only scanning half your part, then mirroring it, that's totally doable. And it works well for bumpers because they're symmetrical. The only downside to that is if you have any kind of unique patterning feature or unique topological feature that is only on one side, then you would need to take care that you're scanning the side with that feature. For flattening, obviously you don't want to only flatten half of your part and then mirror the part afterwards. That may have unintended side effects. So that's why we mirrored the part and flattened it as a whole.
Yeah. So I think it really depends on the type of part that you're working on, right? I mean, if it's complicated, then you may mirror it. If it's if it increases, you have to make a balance between scanning time and post-processing time. If you scan the whole part, perhaps your post-processing time is lower, but that depends on the complexity of the part that you're scanning.
And it depends on, there's a lot of different factors. The material that you use would have a role in that as well. How stretchy is the material? How expensive is the material? If you're working with a very expensive material and it's very critical that you get the absolute perfect part right away, you might choose not to mirror the part. You might want to take the extra time to scan it. That way you have 100% confidence that the 3D model you're working with is a true representation of the part that you're going to be covering. That way when you do the flattening work, you're guaranteed that you're going to have the perfect fit. So there's a lot of different factors that come into play there. The complexity of the part, the amount of time you want to spend doing it, the material, and so on. So unfortunately, I don't think there's any guide that I can offer for when you should mirror your part or not. It would probably be like a product by product basis.
Yeah, okay, that's very helpful. So we do have a question here from Mohammed about the highlight and the Monarch tabs. So that's a little bit beyond the scope of the webinar today, Mohammed. The Monarch tab, I'll just very quickly tell you that if you were to apply graphics, say for a graphic application of a film that you'd put on, the Monarch tab allows you to flatten the graphics and have the graphics distorted in the same way as the geometry itself. It is a very powerful tool. It is used in paint protection film. You would, of course, need to have a way to get your graphics printed. But if that is an interest of yours, I would encourage you to reach out to my colleague, Mark Jewell, who'll be happy to answer any questions. But it's a little bit beyond the scope of what we're hoping to show people today. I do apologize for that. And in the highlights tab, Luke, if you just want to talk a little bit about the highlights tab.
Yeah, these are just different visuals that you can turn on or off that help with the flattening process. So one of the things we tried to fix early on was the fold or wrinkle that appeared in the top corner. Sometimes if you're working with a very complex mesh, it might be difficult to see them. So what we can do is we can turn on or off our strain map here. So that's going to turn your mesh basically in black and white. And we can also turn on or off the edge highlight here. So even though it's off, Rhino likes to display the triangulation of the mesh. So sometimes you have to pan around a bit, but you can turn that on or off, and that makes it very easy to spot any kind of defect or fold or wrinkle that may be in your mesh. And there's different highlights too. So we can turn on or off the piece ID number there. We can turn on or off the grain line and so on. But these are simply just, they don't affect the quality of your pattern. They're just different visualizations that potentially help you achieve your goal faster.
Yeah, if you're doing a lot of scanning and if you're doing a lot of patterning and a lot of templates, say you've got a dedicated area for making templates and you want to go fast, then your technicians will come to a place where they choose the highlights that are suitable for them to get their job done more quickly. And the highlights tab just gives you a bunch of flexible options. Okay, so we have another question, and this is from Mike. So in general, the most time spent in all the projects is cleaning up the mesh from the initial scan. Well, that is true sometimes, Mike. It's not true all the time. You will develop your own scanning technique and you'll become better at scanning. And as we mentioned, one of the big 5 best practices is scanning technique, where you are going to orbit the scan surface approximately 30 centimeters away. You'll keep the scanner in constant motion. And with that constant motion, you will not overscan or you'll not underscan. You'll be sensitive to areas where there's, say, pits or ridges or things like that. Areas where the bumper comes in, meets up with the quarter panel, for example, where there's a slight gap between surfaces. And you'll get better at it. And the better you get at scanning, the more you'll reduce the post-processing of the scan. So it is certainly the case for beginning scanners that they may have some, a learning curve, and you have to develop your post-processing technique. But once you become good at scanning, you'll reduce the amount of time that you have to spend post-processing. And also, once you become better at it, the post-processing workflow will get faster and easier. So I don't know if that helps. If you want to know more, we can certainly help with helping to understand the trade-offs between good scanning and post-processing and that kind of thing. All right, the next question is from Jill. And the question is, when using the target strain tool, does it decrease the scale of the part, including the boundaries? And are the boundary dimensions decreased by a percentage? Luke, do you want to take this one?
Sure. So when we use the global target strain, we have the option to apply either primary or principal or transverse strain. I chose principal strain, which is in the direction of the grain line. So I essentially compressed the part from side to side when I applied that strain. And it's compressing that part of the pattern by about 2.5%. Transverse strain is the opposite, is perpendicular. So I didn't do any transverse strain, so we didn't compress it in that orientation whatsoever. So it's just an easy way for you to compress your part to apply a strain to it, such that you'd have to essentially stretch your part by 2.5% to get it to fit the surface area of your original 3D model.
Yeah, the target strain tool essentially injects strain into your part. It is putting the strain in by an amount that you dictate and in a direction which you dictate. So when the dimensions are changed, it's dimensions across the whole part. The boundary dimensions are decreased by a certain percentage. So if you look at the transverse area or the lengthwise area from left to right, say from headlight to headlight, that distance is going to be shortened. So you can use the target strain in a way that makes sense. And again, for some film, it's not meant to stretch. For other film, as paint protection professionals, you guys know that it is required to stretch, or typically does stretch as you apply it. Okay, the next question here: is there any training that comes with the purchase of Exact Flat? Sorry for all the questions. I've been pondering. I've been pondering. I can't even read your word there, Mike. Pondering. I'm just going to say pondering purchase for a long time. So yes, it does include training. The training is done by us at Exact Flat, and it's done online. And typically, if you are an experienced CAD user, you can get up and running with Exact Flat in about an hour or two. So the training is very quick. It's very easy. It's pretty straightforward, and we can even make available what we call evaluation licenses, in which you pay a small fee. You get a training technician that will train you on how to use it. You try it out for yourself, and then that way it can help you make a decision. But I will vouch for one thing: it's an easy product to learn. Okay, next question is about decimation. What is a good number of triangles to get the job done? It's from Antoine. Thank you for the question, Antoine. And Luke, I'm going to hand it back to you.
So when you're working in the Peel software, you want your output mesh that you're sending to Rhino to be, generally speaking, I don't recommend any more than 500,000 triangles. One of the first steps we do in Rhino is our adaptive remesher, which will automatically decimate the mesh down to a level that Exact Flat can work with, and it operates based off of the curvature. So there is no right or wrong answer there. You want to give enough information to Exact Flat for it to build its curvature map, so it can Exact Flat can decimate the mesh properly. But the decimator in Exact Flat, the adaptive remesher, is purpose built for Exact Flat, so it's going to decimate your mesh in a way that is purpose built for Exact Flat to flatten. So yes, the Peel software does have decimation features, but I would recommend using the Exact Flat adaptive remesher instead, because the mesh that you're going to get out of Exact Flat is geared towards Exact Flat. It's got some key characteristics that work extremely well for flattening, so you tend to get a better mesh out of that. So okay, there's no right or wrong answer. I would say the sweet spot's probably 250,000. That's usually where I go, but it depends on the size of your part and what you're doing.
All right, look, I just want to clarify for the audience out there. So you can decimate in Peel, in the Peel software, but that is not recommended. You want full fidelity of the mesh coming out of Peel. Is that correct?
Yes, correct.
And then when you get it into Exact Flat, then you can condition the mesh using the Exact Flat tools to make it optimal for creating a flat pattern, right? So prior to Exact Flat, let the mesh be, use all the detail. And this is also, I just say, one reason why you don't want to overscan. Overscanning essentially adds more polygons and complexity to your mesh. So it's another consideration here. Okay, I know that we're running up to our time limit here, but there's a couple more questions. If you guys just bear with me, we'll try and get through them as quickly as we can. Okay, next question is from Derek. Can we review a situation where the strain creates a situation where a seam or a relief cut will be required? Yes, we can do that. Unfortunately, we're not going to be able to do it right now, but we did not demonstrate relief cuts, but that is a feature of Exact Flat that makes it very powerful for creating paint protection wraps. So Derek, if you have a question about that kind of stuff, I'd encourage you to reach out to Mark and his team, and we'll be happy to talk more about that. Okay. Next question is from Adam. Were those cutouts in the bumper just projected from their 3D shape onto the 2D version? Those cutouts also have to have shrink to accommodate the stretch. So Luke, there's two questions there. One is, how did you create the cutouts? And the second thing is, are the cutouts shrunk in the same way as the rest of the geometry using the target strain tool, such that they will be properly sized when stretched?
Yeah, so the cutouts, they're 3D curves directly on the surface of our 3D model, and we used the trace tool, that's this one right here, to essentially trace and flatten those curves onto the 2D patterns. They're not simply projections, they are physically mapped from 3D to 2D. So any change I make to my 2D pattern here, we're going to see that reflected with the shape of the curves here. So if, for instance, I were to use a different pre-flattener, and what the pre-flatteners do is they take the original 3D shape and they give you some kind of initial unoptimized 2D flat pattern. But as a demonstration here, if I were to use a different pre-flattener, I will also see these curves distort to match the current curvature of that mesh. So let me come back over here. So we can see that they've deformed and they're hugging on and they're tied directly to the shape of that piece. If I were then optimize again, we'll see those curves again following the shape of that mesh and they're unfolding and following the curvature of that mesh as I optimize. So it's not just the projection, they do shrink and expand and contract with the shape of the mesh as you, whether you're optimizing to no strain or whether you're applying target strain to the pieces.
Okay, Adam, I'm hoping that answers your question. If you want to know more about this, we're happy to talk about this in more in detail. The reality of the exact flat flattener is it's not a projection flattener. What it does is it actually distorts the 3D object through nonlinear transformation or deformation into your 2D pattern piece, such that when you wrap it back on, it fits perfectly. So the cutouts have to go through the same deformation process in order for them to be properly applied. And what we've done is we've made a trace tool, as Lucas described, and that trace tool will allow you to trace features. The trace tool is used in a whole variety of contexts. It'll be used, for example, in this situation where you want to trace cutouts. The marine industry, they trace chine lines on a boat, or markings for marine canvas, or a whole variety of things where you want to translate a point from 3D to 2D and get the exact point or a line or a curve or whatever it might be. Okay. Adam, if we didn't answer your question fully, though, please do reach out to us. We're happy to do so. Okay, the next question is from Chris. So the question is, this comes out as a DXF file and probably being opened in AI, which I assume is Adobe Illustrator file or similar. Then I'm guessing edits are also made in Adobe Illustrator, and are all the edits done in ExactFlat? Well, it depends on the type of edits that you're talking about, Chris. So first of all, we can produce a DXF output, and a DXF output is a layered file made for cutting tables or plotters, or we can produce a PDF. Both outputs are available to you. You can then either plot your output files on paper and then cut them out with a paper template, or what you can do is if you have a cutter or you're going to send it out to a cutting service, is you can send the DXF itself out to be cutted on an automated cutting table. Either option is available to you. Now, with respect to edits, I'm not sure what edits you're talking about. If you're talking Adobe Illustrator, and for example, if you're making edits like graphics and things like that, the graphic edits are not backwards compatible then into a DXF. You'd have to create your output file from Adobe Illustrator and then take it from there. We can make edits to the 2D file here, so you can put in like a dart or a cutout in 2D. You can do the darts or cutouts in 3D, and in fact, they're usually done in 3D, and then they're automatically sized when you flatten the part. So I'm not sure if I've answered the question, Chris, but if you have want to know more details about this, again, I'd encourage you to reach out. We're happy to clarify. Okay, so another question from Mike. So, I would like you to address the new module of VX Elements that flatten. It's free, but anemic. Okay, so we don't like the word anemic, sorry. Sorry for the, objection to the language, but I will say this, Mike. ExactFlat specializes in what are called non-developable surfaces. These are surfaces that have compound curvature in multiple directions. There are a lot of flatteners. You can choose from the marketplace. Rhino has one, SolidWorks has one. There's no shortage of them. The problem is that you want an accurate template, and if you have curvature and you want consistent accuracy, then you have to choose a program that is able to give you consistent accuracy. My understanding of the VX Elements flatteners is brand new. and it's primarily for more developable surfaces. These are surfaces that only have a curvature in one direction. So that is a point to take into consideration here. You'll need to make the right assessment for yourself in terms of what types of things. If you're doing cylindrical or if you're doing non-developable surfaces, you'll have to test it and make sure. What I can tell you about the Exact Flat flattener is that it has been used for more than 15 years in a lot of different industries. In fact, about 60% of the light passenger vehicles, which means cars and trucks around the world that are produced today, the dashboards are produced using Exact Flat, and the dashboard textures and A-pillars and things like that of all the new cars. And we expect that number to go up over 80% in the coming year or two. So the confidence that we can communicate and we can convey to you in the accuracy of the patterns is without question. You'll need to satisfy yourself, and we're happy to make those demonstrations and even give you a way to do that. In addition, there's other things like putting in darts, the target strain, and these types of things, which are part of making a great set of templates and a great set of patterns. If you're making templates, especially if you're making templates for resale, they're going to be installed by customers. They'll want to have confidence that it's the right thing. And OEM providers, like, I'm not going to name them, but it's like 15 or so OEM providers of the film. They're users of Exact Flat as they are today. Hopefully that answers your question, Mike. If you want more information, again, I hate to be saying a broken record, but please do reach out to us. Okay, next question is from Chris. Fitment adjustments. So I'm not sure what you mean by fit adjustments. If you have scanned your part, properly, and scanning is pretty much foolproof. The scanner that we've shown you here has accuracy to 0.1 millimeter, or maybe even 0.01 millimeter, which is more than enough in terms of the accuracy that you need for this. You do not need more accuracy to do this type of work. The film itself has inherently got some stretch to it, and it is just fine. In fact, yes, it's 0.1 millimeter. So generally speaking, you don't have to make adjustments to fit. If the scanning is done properly, it'll fit. Okay, next question. Is Exact Flat used in the metal forming industry? Are there material settings already available for this? So the answer to your question is yes. If you are making metal or thermoformed objects, you can use Exact Flat. There are a couple of other considerations. First of all, you need to get your material tested for the type of stretch. Metals are generally isotropic, so they will stretch the same in all directions, but they may have a thickness. And so the only nuance when you deal with metals is to deal with things, you have to have the plane of flattening. Is it the inside surface, the outside surface, or is it the midpoint or some other point in between? That's a consideration that you need to take into account. If it's thicker metals, if it's thin metal like a sheet metal, it'll work just fine. So if you have a question about metal forming, Shane, then we're happy to talk more about that. But yes, it can be used in metal forming. Okay, so next question is from Alex. Once the pattern is flattened, should I double check the fit before sending it off to be cut? What are the odds that the pattern is not 100% to scale? Well, I would say that there's a couple things you can do here, Alex. So first of all, you're raising a great question. You have to have 100% confidence in the output. Otherwise, you got to check every single output. If your output is only right 95% of the time, you got to check every single time, which is a lot of work. So you can measure perimeter edges in 3D and 2D. That's one way of checking the fit. You can measure surface area between 3D and 2D. It's another way of checking the fit. You can print a paper pattern, plot a paper pattern, cut it out, wrap it on the object in question, and you can see how it fits. And as you get confidence that it's going to work 100% of the time, then you don't need to get it tested each time you go off to get it cut. And we have customers that have the exact same concern that you have, Alex. So trust me, this is not a bad question you're asking. We can confidently say that we stand by Exact Flat and its accuracy, and particularly in complex situations. So there are things that you can do in advance as you're getting to know the product to satisfy yourself of the accuracy. Those things are pretty simple. They're pretty straightforward. And you are right to ask that question because many do. But we're very confident in the capabilities of the product. It's been proven over 15 years and in so many different situations. So if you want to know more, Alex, then you can give us a call. And Mike, thank you very much. Thank you for bringing them over in SEMA. So yeah, looks like I have answered all the questions. If there's more questions, I'm happy to take more questions as a follow-up to this session. I do think this has been a great session. I thank you. You know, one thing I'll say, oh, actually we do have one more. I'm just gonna get one more in from Alex right here. If I'm scanning a front bumper, hood, and fenders to wrap using printed graphics, how can I check my graphics will line up on all the parts before printing? Well, that's a great question too, Alex. So the graphics have to flow. We call the flow between one panel or one pattern piece and another pattern piece. They have to flow accuracy and be perfect. And you can check that by doing what we call walking the pattern. Now, this particular example we showed is only one pattern piece, but we do have a tool in ExactFlat where you can actually walk the edge of a pattern between two adjacent pattern pieces, and you can visually confirm that there is flow between a left and a right piece or a top and a bottom piece or so on, or even 3 or 4 pieces that come together. But that is an excellent question, Alex. And yes, you can check it visually. And once again, not to belabor the point, we're happy to talk about that in a session. If you want to give us a call, we can go through more of that. And I think we've got some videos which we'll send out afterwards on graphics that flow across pattern edges. Okay, I'm going to stop it there. I want to thank everybody for taking the time today. If you have questions, I'll just say we have a 3-part process where we can review what you're currently doing today and your current workflow. If there's an interest, we can propose a new workflow, whether you have graphics or whether you're just using straight up paint protection film or other types of vehicle wraps. And then we can review the implementation with you. We do work very closely with the Peel3D team. The Peel3D scanner we can vouch for 100%. We have used it ourselves. We've used it for clients, and it has more than enough accuracy. The ease of use is there, and once you become acquainted with its features, it is a very robust solution for this particular application. So I will just stop there. Libya and Marie, I'd like to thank you for inviting us to be guests on your webinar today. I think that we had some great questions, and if there's anything more that you'd like to add, we can stop the webinar there.
Thank you. Thank you, Ethan. I hope everybody hear me, and I'm Libya. And great questions and great webinar. Thank you to you, Ethan, to Mark and Luke. It was really great. Looking forward for the next one, Ethan. Thank you.